For my science fair project, I wanted to experiment with roller coaster physics by building my own mini roller coaster model. I got help from my friends Nate and Rachel Holyoke, who are engineers at Orbital 8TK. It turns out roller coaster science is a lot like rocket science. We used a Connects roller coaster kit for the model and a Starburst candy to represent the human rider. With the right physics, the Starburst rider should stay in the car while going through the roller coaster loop, even without a restraint. As you'll see, we managed to make that work, but the rider still needed some restraint during the initial vertical drop, so we taped him in from the bottom. When inside the loop, there are two forces acting on the rider. One is the force of gravity, which pushes down on the rider towards the earth. The other is the centripetal force of the loop itself, which pushes outward against the track as the rider travels around the loop, and gets stronger or weaker with the velocity of the rider. When the rider is at the top of the loop, centripetal force pushes up directly against the force of gravity, which is pushing the rider down. At the top of the loop, we need the centripetal force of the rider to be equal to or greater than the force of gravity. Here's our equation for centripetal force. And here's our equation for gravity. A little math gives us the equation we need to determine the rider's velocity. The radius of our track is 6 inches, so plugging in the acceleration of gravity tells us that our rider must be going at least 4 feet per second, or about 2.7 miles per hour at the top of the loop. Even though gravity works against us at the top of the loop, gravity can work for us to get the rider up to speed by dropping the rider from the right height at the start of the ride. When an object is dropped, the distance traveled by the object is calculated like this. The velocity of the object is calculated like this. Solving for time and inserting it into the dropped object equation gives us this. Plugging in our velocity of 4 feet per second, we know our drop height needs to be 3 inches. But we must also account for the height of the loop itself. Since our rider will decelerate as he climbs the loop, we need to add the diameter of the loop to our drop height so that the acceleration of the drop and the deceleration of the climb cancel each other out. The diameter of the loop is 12 inches, so our drop height is now 15 inches. In our initial tests, the Starburst rider dropped from 15 inches still fell out of the car. Why? Because our model track introduces friction from the track itself and from the air. We also realized that we didn't account for the length of the track to get from the drop to the loop. Even though it's small, there is some deceleration as the rider moves along this piece of the track. Through experimentation, we found that the right drop height for our Starburst rider traveling along the Connects track on the kitchen table was about 20 inches.